extract over the train and the test set. And finally, we gathered data from a bunch of existing sources. So these were sources that had either collected parallel data for like tutorials or for religious texts and other things. And we gathered them together. We applied these data cleaning heuristics, and then we split them into these splits of train, validation, and testing. And the other thing that we did is because we wanted to evaluate how well our models would do after pre-training. So we would take, say, how much data we had, and we would see, initially we were thinking, okay, we're going to use data for pre-training. It's very, very little. So what we did is we created something called pseudo-monolingual data, which we used for further pre-training, which we'll go into in a future section. So pseudo-monolingual data is this way of like getting away from having very, very little gold data and going to a large amount of pseudo-monolingual data, which is model generated. So first is just going to have a little overview on previous approaches to pre-training multilingual sequence-to-sequence models. So a very popular one at the time, and even like other variants such as T5 and so on, use this sequence-to-sequence masked language modeling approach, wherein you take an input, you add masks, and then you look to reconstruct it in the output. So this is similar to BERT, except it's happening for sequence-to-sequence models. And the MBART paper did this. They did this in the multilingual setting by extending BART. And per language, they had 1.6 gigabytes to 200 gigabytes of data per language, and then they pre-trained on this. And they had large improvements on machine translation over using random initialization. And one thing to note is even the low resource languages considered here, for example, Sinhala, they had 1.6 gigabytes of gold data, which is very, very, very high resource compared to the low resource languages that we're considering here. So in our paper, we called our approach AfroBART. First, we used bilingual dictionaries extracted using word alignment. Wait, this is where? Hello. Okay, so first we use bilingual dictionaries extracted using word alignment. So this would be, for example, with English and Swahili, we'd find a similar word that would exist in the Swahili corpus. So in this case, we have the word for like sandwich and the word for eat. And then we'd augment high resource language data with data from these low resource language dictionaries. And in this case, we mean dictionaries simply to be words that are aligned in one language and then aligned in the target language. So for example, we'd have this sentence of like Bob was eating a sandwich. We'd use our dictionary to replace some words. And then we'd have this augmented high resource, low resource language data using our dictionaries that we would be able to use to pre-train our MART model. So for pre-training in this like extremely low resource language scenario, especially since we're not considering low resource languages as an afterthought, but rather we're looking to pre-train directly on them for the sole purpose of getting better performance on low resource languages, we devised this sort of cyclical process in which we start from monolingual corpora, we use this dictionary augmentation phase, we do an initial stage of pre-training, then we fine-tune on our machine translation corpora, which allows us to have semi-decent machine translation systems that go from English to given target languages that we care about. And then we can translate some more high resource language monolingual corpora, feed that back into the monolingual corpora, and you can go in a cycle. Now this sounds amazing because you can keep going on and get unlimited performance, but that's not exactly how it works. We do 1 or 2 cycles, and that's where we find to saturate performance largely. So in this case, we had some interesting results. So our pre-training setup was, at this time, very decently sized, but now extremely small, 85 million parameter model transformer base architecture. We used around 30 gigabytes of data, and we trained on 32 V100s per day, which was much less than comparable models at the time. And we evaluated using Sacre Bleu and the character engram F-score, so we could have more fine-grained information on the output of our models outputting morphologically rich languages. So one thing to note here that our models, so our AfroBART models, seem to do much better than, say, random initialization and multilingual machine translation baselines, which sort of goes to the point that we can actually do some sort of pre-training for low-resource languages, and it does work to some extent. And we have, this is sort of promising, especially with this slide, where we look at the number of parallel sentences we have when fine-tuning on machine translation and their corresponding performance. And we can see that we need 5 times less fine-tuning data to replicate the same performance of random initialization. So it shows that we should be focusing on pre-training, and even with the limited low-resource languages that low-resource language data that we have, we should see how we can get some of this or use some techniques in pre-training such that at fine-tuning time, when we want to adapt to a specific task, we only need to curate a small set of very high-quality data relative to gathering a lot more, and then we can fine-tune that and still replicate better performance. So from this, it was very simple. We had a reproducible benchmark for these 8 African languages. We had these 2 new pre-training techniques for low-resource languages, and this was like low-resource focused pre-training. And finally, we had in the paper noun class analysis on selected languages, and this was able to show that we were actually improving on multiple axes of quality. So some thoughts on this is that there's a lot of effort, very important work on gathering new data sets, but it's also important to look at the data sets we have and look how we can repurpose and improve them, because there are actually a lot of interesting things we can do. And also seeing what are the issues with the existing data sets and how we can make them better for future usage. And another thing is simple things like dictionaries, which are much easier to gather together than more parallel sentences, allow us to inject a lot of parallel information at scale despite limited data. So given that we have parallel data, so we have a lot of this machine translation data in these languages, can we use parallel data in pre-training more effectively? So this was work done with Miguel called Paradise, and this was how we looked at, can we augment the existing BART objective but add parallel data in there and see how it affects cross-lingual training transfer performance. So just a brief background on multilingual pre-trained language models. This is a diagram from the XLM paper, and essentially you take a sequence of tokens in a given language, you mask them, and you learn to predict them, and that is sort of your self-supervised objective that allows you to get a lot of signal from pre-training data. And this was extended with translation language modeling by the folks here in the bottom, where you have, say, one sentence in English, the corresponding sentence in French, and you do something similar, and this showed to improve cross-lingual performance somewhat. So with BART, this was extended to low-resource, to sequence-to-sequence models, where you have your encoder, you mask some stuff in the encoder, and then you generate the full sequence in the decoder. And they had better performance on generative tasks, and this again was extended to multilinguality with MBART. But the thing with MBART is that they only use parallel information at fine-tuning time. So here I say like they showed improvements on downstream machine translation and showed large gains over random initialization. However, this was doing pre-training without any parallel data or without a lot of it. And they only induced this parallel signal at fine-tuning time when they were actually fine-tuning on machine translation. So can we use parallel information to help sequence-to-sequence pre-training? So enters Paradise, which stands for this below. And we look at ways of integrating this parallel information, this parallel signal, which we actually have a lot of with respect to actually how much monolingual signal that we... Okay. Hello? Okay. We have a lot more parallel signal in a lot of low-resource languages and a lot of monolingual signal, because a lot of the text or the digitized text that's produced in these languages are usually for translation. So can we integrate bytext, and can we introduce the dictionaries that were introduced earlier for improvements on cross-lingual modeling performance? So first we introduce bytext denoising. So this takes advantage of using sentence-level machine translation data, and it sort of augments the existing BART style objective. So you take a given sentence. Here, this is a sentence in Japanese. You mask some tokens in this sentence, and then you look to decode it afterwards in English. And this sort of adds some regularization when doing this machine translation style objective. And it allows us to not overfit to very, very small data sets, which is what we have in the case of a lot of our low resource languages. The other technique we introduce is called dictionary denoising, and this is where we use a multilingual dictionary. So in the case before, we only would have a dictionary that went from, say, English to Swahili or English to Afrikaans or something like that. Here we can actually use English as a pivot language. So we can say, okay, all these words in all these languages map to this word in English, therefore we can use English as a pivot language. So we can actually use this multilingual dictionary to noise our English data and data in other languages. So here, when we do dictionary denoising, we take the original sentence, their work is absolutely amazing, and then we can slot in a word in Japanese, a word in Arabic, and a word in French with some masking, and then we can use that as a training objective as well. And so this is like a way of sort of cross-lingually corrupting our input. So the end objective is a mixture of these three objectives. So we keep the original MBART multilingual denoising objective for our monolingual data. We use our bytext denoising objectives to take advantage of the parallel data we have in many languages. And then we also use dictionary denoising to take advantage of even these small dictionaries that maybe are only 5,000 words aligned in many languages. And we apply them at scale to our high resource languages. And the combination of these forms the Paradise pre-training objective. And sort of as for intuition for why this works, if we have this sentence, their work is absolutely amazing, we have three ways of corrupting it. So one of them is using this bytext denoising objective, the other is the dictionary denoising, and the other is like the monolingual denoising, where we'd put some masks in this sentence and then get to decode the full sentence at the end. And you can see here the decoder has the same job. No matter what the input is, they're all sort of semantically similar, and it has to decode. Their work is absolutely amazing. So it's a way of sort of pushing all of these languages, pushing all this cross-lingual signal in sort of the same space where the decoder can say, okay, this sort of kind of means the same thing, so we should decode the same sentence when we're decoding in English. So an analogy with like human second language learning. I like to think of using some example sentences or translation pairs in the dictionary is sort of similar to how we actually learn a second language. So when you learn a second language, sure, you'll have books in different languages, but you'll also probably have a dictionary handy to help you check up words that you don't know, and maybe some example sentences to see how to use text in different scenarios, whereas just shoving all the languages together separately. And it's sort of, you could learn multiple languages, though it would be a struggle by shoving all the books together. But if you have a dictionary and some example sentences, I'm sure your life will be a lot easier. So this is really important. So the combination of a bunch of books in different languages, in this case the analogy to our large-scale pre-training data, and a dictionary, which is just this small list of aligned words in different languages, allows us to really scale this parallel signal at scale. So we can take, say, a small set of aligned words with English and a given low resource language. We can apply this to, say, a terabyte of English data, and that sort of helps our performance and sort of helps expand the coverage of low resource languages seen during pre-training. And to be fair, this is why language dictionaries exist in real life as well, because if we have books in given languages, we cannot translate every book in the world, but we do have dictionaries which sort of help us get a bit closer. So here we have some experiments and results. We trained on 20 languages in this case. We used a similar setting as before, which was 32 V100s for a day. But we did increase, since we had more data than before, to 196 million parameters. And we use about 80 gigabytes of data with up to 23 gigabytes of parallel data included. And then again, this was much, much cheaper, as we'll see, than other comparable models at the time, and definitely much cheaper than models now. So we evaluated on 3 downstream tasks. One is like machine translation. The other is PAUSE-X, which was a paraphrase classification task. And the last one is XNLI, which is a common multilingual natural language inference task. And these are all used for benchmarking the cross-lingual ability of our models and also seeing how well they are at cross-lingual transfer. So here is like machine translation results. And the interesting finding here is, as you can see, like the Paradise does perform much better in all language pairs in all directions. But the interesting thing is, despite seeing the same data, so as I said earlier, the MBARD paper was inducing this parallel signal only at fine-tuning time. We would take that same parallel signal and put it in at pre-training time. And despite seeing the same data, adding parallel information at pre-training helps with fine-tuning on machine translation. And this can sort of be said to some extent that the pre-training data or having machine translation style data that interacts with the large scale of like monolingual data at pre-training time, they sort of work together in a conducive way for our downstream task, especially for cross-lingual settings. The other thing here is we show that this is an ablation of like the different steps we added here. So we can see that increased parallel data definitely does help. And it did help better than scaling just the monolingual data we had here in this setting, at least to a similar extent. And we also find that the dictionary noising, so the part where we scale parallel data cheaply with our dictionaries, is important. And this is actually very important on non-Latin scripts, where maybe these tokens aren't seen as much during pre-training. But with dictionary denoising, we sort of synthetically induce them during pre-training to be seen a lot more, and it seems to help in downstream tasks as well. The other thing we do here is for classification, we concatenate the token in the encoder and the final token in the decoder, and then we use a linear predictor, and we show these like the differences of like fine-tuning techniques on XNLI. And this is good to know because though here we're using, say, encoder-decoder, like the style that is used, for example, in T5 and BART and a lot of these sequence-to-sequence pre-training tests, we can see we actually don't regress a lot on performance when using encoder only at inference time. And this is half the parameters. So from like 200 million, you're going to less than 100 million. So here is XNLI, and we can see that Paradise models do perform quite a bit better. And this all goes to just the showing that if we do pre-train our models to be more cross-lingual and sort of try and introduce this bias at pre-training, it seems to pay off at fine-tuning time in all the languages that we tested on. PAUSE-X, similar story. Here with PAUSE-X, we also compare to previous models that were done, and we also get pretty similar performance to XLMR large. And XLMR large is 600 million parameters, and this model is 3 times smaller and pre-trained on a lot less data. And by purposefully including parallel data at pre-training time, we're also able to get similar performance. So here's a comparison with popular models at the time. And we can see here, I think the most important stat is obviously like the performance is on par, but also we see the amount of compute that was used for pre-training. And we can see some of the models that we achieve very close on par to have been trained on like 100 to 800 times more compute than our models. And our models are much, much cheaper to use simply just because we induce this parallel signal at pre-training time. And also we compare with the original MBART, which is 3 to 4 times larger on machine translation. And we show that for a lot of the mid to low resource languages that we test on in this case, we perform similarly. But the place where we do have a bit of a larger discrepancy is on the English to Spanish task, where they had 13 million fine-tuning sentences. And this is largely an artifact of scale that's happening here. So 200 million parameters perhaps cannot scale to high resource workloads, but if we do purposefully use them in low resource workloads, they can benefit quite a lot. So one takeaway that I recommend to anybody pre-training any multilingual models or training any multilingual models is use parallel information at pre-training time. And also don't constrain parallel data to only be translation data. Like you can use dictionaries, look at other types of parallel signal that you can get. Cross-lingual transfer is really something quite neat, and we should take as much advantage of it as we can. And the other things with dictionaries, even for the lowest of low resource languages, if we can get some aligned information with English and another given low resource language, they can add parallel information very cheaply, and they also help during fine-tuning time as well. And this was also replicated in a setting with arguably even lower resource languages, where in a follow-up paper with a student, we tried this on low resource languages in the Americas, and it also was able to improve performance there. So this is all not very ChatGPT, not very Llama. So going back to LLMs, how well do our current LLMs perform on these things, on these languages, in these settings? And an initial work on this, which is under review, is on exploring methods for adapting LLMs to low-resource African languages. And this is by Stephen from Ames. And first, few-shot prompting LLMs for machine translation works surprisingly well. So you can simply do this, English, French, English, and then just say French, and you'll get a semi-decent French sentence. However, oh yeah, and this is super data efficient. Like this is one shot. So you only need one example to sort of draw this information out of the model, and it seems to work quite well. Like this is on par with models that are fully fine-tuned on English to French translation. But for low resource languages, this isn't as simple. If many language models struggle to even continue to generate text in a given language, even if they're given a lot of context in the language, and much less translate in a few-shot manner. And there are many issues. For example, when few-shot prompting from English to Kikamba, the translations would always end up being in Swahili, which is an issue with our models and just shows that we really should be having low resource focused efforts where we actually pre-train models and care about these languages. So another interesting thing here, we tried few-shot prompting a bunch of models in different degrees of like resource languages. We tried the OpenAI TextDaVinci 2, TextDaVinci 3 models, and also used the NLLB models. And we can see, though NLLB seems to maintain performance or gets decent scores, the TextDaVinci models, you can see the drop is quite stark. And though some may say the comparison is a bit unfair, because the NLLB models are fine-tuned for machine translation, TextDaVinci 2 and TextDaVinci 3 seem to perform decently at the high-resource languages, but then drop to close to 0 for our low-resource languages. So these large-scale models that are being publicized, right now, they really are not our best option for a lot of low-resource languages. The interesting thing here is we did a human evaluation of the outputs of the models on different sets. So we did the Flores 200 data set, which we saw in the previous slide, and humans did tend to prefer NLLB over TextDaVinci 3 and TextDaVinci 2 cases. Note that TextDaVinci 2 for Kikamba, everything sucks pretty much. It's all 1 stars. However, with NLLB models, even on data sets that are relatively out of distribution, such as the real-time QA data set, which is new data that's being produced every day for question answering, we fed that to our machine translation systems, and it seems like the smaller fine-tuned variant still wins for a lot of these low-resource languages. So how do we fix this? There are a lot of cool things that we see with these large language models, and it would be nice to have them in a lot of low-resource languages as well. One thing is there is clearly a data issue. The nice thing is that large language models, if we fine-tune them correctly, they tend to do well at generating task-specific data for various use cases. So could we use large multilingual models that are trained for these specific cases to help us generate data which we can then use to distill to smaller models? So this is an example from a paper last year on how folks used GPT-3 to generate a better data set for NLI that was better than ones that humans generated. Also, qualitatively, LLMs generate with far less quality in non-English languages. So I surmise that translation will be important. If we can get translation down, I think it will unlock a lot of capabilities in these languages. So here's like internet usage by country, and the power of language models is that they can really take advantage of the scale of data that we have produced and put out there on the internet. But for low resource languages, that may not be the case, because unless we wait for the amount of text data and the amount of speakers of these languages to multiply, and then use the internet in these languages, and then develop language equivalent services, we're probably not going to get there naively by just crawling the data, pressing a button, and hoping that it will work. And another thing to note is that especially if you are bilingual, you speak one of these languages is maybe not as well represented, and you speak English. If you're using the internet, you're probably going to use English most of the time because the quality of content on in English is just much, much better, and this sort of feeds into this problem more where you have like a greater dominance of English being a language on the internet and English data. So we should be doing task-specific multilingual machine translation. I think that's important. I think a lot of our systems are relatively generic, so to say. But if we look to translate for maybe specific subtasks, like learning to translate specifically for summarization, that is an interesting problem to work on and seeing how we can generate better data in that case. Another problem that's interesting is learning to translate and generate data that's actually useful for downstream performance. Another thing is, another neat thing about large language models is that we can learn very efficiently from less than 16 demonstrations, and it seems to do well on various tasks. And we should really be converting the amazing data sets that we've created to instruction tuning style data sets. So instruction tuning style data sets is where you like ask or few-shot prompt to prompt and response, and then try and adapt open source language models so we can interact in the same way here. So this will sort of leverage cross-lingual transfer if we co-train on English data, and also go from prompt and response. So we can leverage instruction tuning, not for only English-only languages, but for low-resource languages as well. It's something that hasn't been tried as much yet, but we definitely should do this at a larger scale and publish these models and try things, see what works, see what doesn't work, and so on. So we really get an idea of how well low-resource languages interact with large language models. So like, for example, with like the great Mazakane data sets, like Mazakane News, we could make it instruct Mazakane News so we can have instructions there and see how well we do in these languages. One thing I recommend that everybody does is just like play with language models, like play with them a lot, see what they're very bad at, and see, like gain intuition on what they're not good at. Like, are they not good at speaking your language? Are they very bad at summarization of articles that talk about a specific topic? Like, do they hallucinate when you mention something that's very locale relevant? Like, play with them, see what they suck at, and then create data sets to solve this. LLMs are really sample efficient, so we should be looking at using this to our advantage and creating like small, high-quality, language-relevant, cross-lingual instruction tuning data sets, and seeing how far we can push large language models, low-resource languages, and cross-lingual transfer. Thank you.
Thank you. Any questions? We have time for 1 or 2 questions. Okay, I'll go to Kathleen, then come to you.
Thank you for the presentation, Marshall. You mentioned that if we naively wait for there to be more data available for low-resource languages, it's likely to not happen. But have you considered what risks are involved with using LLMs to generate data for low-resource languages? Thanks.
I'm an empiricist in some sense, and I think one thing that is cool, especially if we open source these models, is we can see how bad they are at certain things. I think right now it's a big unknown because a lot of people haven't tried it. But I think we should try. We should try using LLMs to generate data for low-resource languages. If it works, great. If it doesn't work as well, we should think about why it doesn't work, how it doesn't work, and then look to fix that. But I think that if we just wait for data to be available, that's sort of a problem on the opposite spectrum because we're not able to develop technologies and tools that are useful for people working in this space and that could benefit a lot from having models or systems that work well in these low-resource languages.
Okay. I'm curious if you have experimented ways of using low-rank, like fine-tuning techniques or like other efficient fine-tuning techniques on low-resource languages and like what the impacts of that would be?
I think, so they work quite well. I think right now we need to think about data. I think it all comes back down to data. So like LoRa is a very nice way of adapting models to new tasks, new settings. But if we have a model that's really not good at using low resource languages in the first place, I think we need to gather data and then combine it with efficient techniques such as LoRa. And I think we can find something that works well in that intermediary. But I feel like current open source models, they're very, very bad at low resource languages, especially the large language models in that case. And I think we should really come together as a community and think of like, what is bad? How can we fix it? Maybe LoRa is one of the ways to do that. Maybe we should be full fine-tuning, then doing LoRa on top. I think there's just like a lot of fun experiments to run. We should try them all and then see what sticks.
Thank you. Thanks for the presentations. Great work, Michelle. I had two questions. The first is just a simple one. I failed to catch the publisher on the last paper you shared, the one from Ames. Maybe if you could go back that later. My second question would be on, I think, creation of loanwords, terminologies that that are transliterated in low resource languages, because this being the case in mostly conversational settings or not, non-formal settings, casual conversation that we usually don't use, or we often even sometimes lack terminologies for some words from high resource languages. Is there any work you're exploring in this area or any kind of advice or techniques you'd have to approach this? Thank you.
Hello? Okay. So for the first question with the publisher, do you mean like the first author? The second author? Oh, I mean, like the first author is the person who wrote that paper. So his name's Stephen at Ames. And with the second one about loan words, I think I haven't done work on it specifically. I've just been seeing how to like get language models to sort of work better in a more generic sense. But I do think it is quite interesting. And I think like maybe I've been biased a lot recently with like working a lot on large language models, but I think the answer to a lot of these questions is gathering data and seeing more efficient ways of gathering data. I think there are a lot of things where it's like we can speculate about them, but if we don't try and gather data, we don't try and tune models, we don't see what works and what doesn't work, I think it's going to be harder to make progress. So I think we should gather data. I think this is very relevant, so we should gather data where people are using loanwords appropriately. We should train models, we should inspect this data, and then see what's bad about this data, what's bad about modeling with this data. Does it confuse the models in ways that we don't want it to, and then look to fix that iteratively.
Thank you. Let's give him another hand of applause. If you do have any other questions, please, you can get him over break. We can continue. Our next speaker is online. Her name is Orevalgane Ahia. She's a PhD student in computer science and engineering at the University of Washington, advised by Noah Smith and Yulia. Previously, she was a research engineer at InstaDeep, working on AI solutions for enterprise clients, and her research interests includes topics like multilingual NLP, model efficiency, and model interpretability. She's gonna talk to us about subword tokenization in multilingual LMS. Give her a round of applause. bear with us as we set up.
So am I to share my screen or like share my presentation myself?
It's already shared.
Oh, okay. I see. Okay, so I'm not the one navigating.
Oh, I think maybe you can share.
Okay, I think that would be better. Okay, awesome. Yeah, so can you see my screen?
Yes, I can, sir. Yes, I can, Mama.
Awesome, thank you. Just a second. Oops. I'm just gonna get rid of this. Yeah. So, hi everyone. So my name is Oriva, for short. And like Evelyn had mentioned, I'm a PhD student at the University of Washington, working with like two incredible supervisors, Noah and Julia. I work on multilingual NLP model interpretability. Recently, I've been interested in like, tokenization algorithms. I, really wanted to be there in person. I had planned to be there in person, but, due to some unforeseen circumstances that I couldn't circumvent, I have to give this online. And I really appreciate the organizers for, agreeing to let me give the presentation online. So today I'll be talking about subword tokenization in multilingual language models. So it's a topic that, that's, usually neglected because people think that, tokenization, is just about preprocessing text and yeah, it's a solved task. So I will start. So first of all, we start with how, how models represent language. So majority of the data in NLP is text. Like a lot of people work on text. We have more data sets on text. Like we have like lots of text on the web, lots of text being used to train like large language models and all. But machine learning models, cannot operate on text in their raw form. We need to like preprocess this text into numerical form. And I mean, this applies to like every like data that you want to train a model on. So usually in order to learn representations over this text, you have a sentence, you don't just like, feed the sentence into your model. What happens is that like this text is split into atomic units, and this term is called tokenization. And each atomic unit is represented by a unique number, and the model learns representations over this. So if I have like, certain words, like I have like a mapping such that if I had a sentence that like, okay, I'll just, yeah, if I had a sentence like, oh yeah, Masakani is so great, I have like a mapping from that maps like a mapping from Masakani to say like some number, and then my model learns representations over this. So what are these tokens, and what determines how a text is decomposed? So like until a few years ago, NLP models operated over words. So if I had like this sentence, Asakana NLP is a great community. Before I feed it into my model, I would do some preprocessing, but I would split based on white spaces or based on punctuations, and I feed like each of these word individually into my model. So what happens is that like with tokenization, you have like the model typically has like a vocabulary that it learns representations for. So like each word in your pre-training data or in your data sets would be represented in that vocabulary. But I mean, what happens typically is that, if we check like all of the words in our data sets, we have like very similar words that have like that share semantic meanings, and these words might like have different representations in the model even when they shouldn't. Like they should probably have like a word like community, and community should probably be like very close or should even like point to the same thing in the embedding space, but they would have like different representations. Another thing is that your vocabulary could also end up being large. I mean, if you have like a very large pre-training data, and you take like all of the words in your data set, like you have like you end up with like a very, a very large vocabulary. And the consequence of this is that like the vocabulary size determines the size of your embedding layer in your model. And the embedding layer, takes up like a large, I don't know what fraction, but it talks about a fraction of your model. And, large embeddings like lead to like very heavy models. So if I had like 100,000 words, then it means that I would have like an embedding of 100K by like whatever like your hidden size is. Um, but we could also say, oh yeah, I can't like train. I can't have like like a vocabulary of 100K. I would just limit this to about 12K, and I would like just take like only the frequent words in my data set, and I would represent this in my tokenizer. And then words that are absent from the vocabulary at test time, I just I just map them to like a certain token that I call unknown. So every word that's like not present at test time gets mapped to like an unknown token. So this is good. You have like a smaller model, and you can still represent stuff like, not accurately, like at test time. But this also leads to loss of information. Like imagine like so many tokens being mapped to like just one representation. Like it doesn't make sense. Like the model like cannot like make like useful predictions on like such tokens. Another issue with like QNKs is that like they're not like generally like acceptable for natural language generation tasks. Like if you have like a machine translation task, you want to translate this sentence to Yoruba, and then or imagine Google Translate just generates this and it has like UNK, UNK. You're like, okay, what's UNK? Imagine you had a question answering task. You're like, okay, what's the first step in making jollof rice? And then the model generates, first of all, you blend UNK. UNK, like you blend tomatoes, you blend potatoes, like what can it be? So like there's a lot of like loss of information with this kind of representations. Another problem is that like for like certain words, for certain languages, it's quite like it's not practical to remove rare words because some of these words are, formed through productive morphological processes. And like removing rare words just means that like you're typically like removing like most of the words in the training data. So then people are like, okay, yeah. So if word level tokenization is, it's not good enough, like let's do character level tokenization. So I have the same sentence here, but here I'm tokenizing at character level. So character level tokenization means that also like please let me know if I'm, going too fast. I could, slow down a bit. So character level tokenization means that we're splitting text at the very granular character level. And then this like drastically reduces the size of your vocabulary such that like you can represent like any like you have fewer or no out of vocabulary words primarily because like dependent on like the vocabulary of the data set. But you can decide to like add all the characters in all the characters for like all languages in the world. And then you're fine at test time. So like words unseen during training, like you can still tokenize them and you can still represent them. Yeah, so this is good. But characters do not convey information as much as much information as words. So if I have an M in Masakani and I have an M in Monisola, like they do not like mean the same thing. There's a lot of like loss of information. And also, character level tokenization is also like, very inefficient due to like the model's limited context size. So models typically have like a limited like amount of like tokens that they can take in. There are like recent methods like Alibi, that try to like, extrapolate to like longer sequences at test time. But like models have like, like this fixed amount of tokens that you can take in. And then when you have like characters, like if I represented this, like I have like if I represent this, I have like 30 tokens. But if I represented this as like individual words, then I probably have like 6 tokens, and that's more efficient. And also like slower inference, like with autoregressive models, you have to like generate like tokens autoregressively. So you have to wait, oh, I'll generate an M and then an A and then an S and then an A and so on like that. So just to recap, so these are like like the drawbacks of word level and character level tokenization. Similar words will have different representations. On the left case, you have like large vocabulary, heavy models, lots of information, long sequences, and all of these, problems. So can we find a smooth transition between like word and character level to, algorithms? That's where subword tokenization comes in. So the principle behind subword tokenization is that like you frequently use words or frequent like words that are frequently occurring in your pre-training data should not be split into smaller subwords. And very rare words can be decomposed into like meaningful subwords. So if you look at the examples on the screen, on the left side, I have cat. And I want to retain like cat as a token in my vocabulary, but I also want, my tokenizer to learn that, oh yeah, cats with the S is a derivation of cat. It's like the plural form of cat. So it's okay if I represent cats as cat and then with the S. Also, with the example of community, like community is derived from commune. Like I want my tokenizer to, or like I want to represent like these words in such a way that, commune is like commune could, I mean, I could retain like the full token, but it's also like accepted to you have these like segmentations that are morphologically like correct, or like a word like diversity, for instance. So in this case, like imagine like I would have like community as like, two separate words. So the way like subword segmentation works is that like, you learn a vocabulary on like a finite set of subword units. So just like every other vocabulary I've talked about, you have like a finite vocabulary because like your model is dependent on that. Like the representations that you learn are dependent on like what your vocabulary is. And typically, like the base of your vocabulary could be Unicode. It's not always Unicode. So it could include characters, that would always appear at test time. So it's possible that sometimes like there's some form of character level tokenization for like rare words. And then this also makes it possible to extract features for novel words. So how are subword units determined? Like there are different ways. You could decide that, oh, I have these rules. Like when I see cats with an S, I split it into cat and S. When I see community, I split it into commune and it, and I like build my vocabulary like this. Or it could be data driven such that, or you use, some method to build your tokenizer and you now like check if like the fragmentations make sense linguistically. It could also be like some heuristics that optimize for faster downstream performance, like byte pair encoding and byte-based byte pair encoding. And these are like the de facto actually. I would be talking about this like more in the coming slides. So like these are like the ones that have come to stay, the last ones in like NLP now. So the fast subword segmentation, what typically happens is that you have like you start with a base vocabulary of only characters, and then you pre-tokenize your words, or like all the words, all the your text into characters, and then you take bigrams. So bigrams are like tokens that like two tokens that like occur like adjacent and are like consecutive. You take like bigrams, you look at like you take like all the bigrams in your text and you look at like the most frequent bigram in the first iteration, and then you add that bigram into your vocabulary, and then you keep on doing this and doing this until you reach like a set vocabulary size. So the difference between BPE and byte-based BPE is that in multilingual models, you have like data, like languages with like various scripts, right? And then the base vocabulary of only characters could be like, very large with like 130K if you're considering like a large number of languages. So like some, like think it was in the GPT-2 paper that they proposed using like, instead of like, starting your vocabulary from Unicode, so like A, B, C, and whatever like number of characters you have in the world, then they propose to use like raw bytes, like UTF-8 bytes, to represent like words. So like you're limited to 256 tokens, and like every word, like everything, every text, like everything could be represented as bytes. Um, so this is good because like this is good because you're able to like train on, like you can train on Latin script languages, and then at test time, like your model is still able to like process text in, say, Arabic script, because like the model has probably learned like representation over bytes, and this has like become the de facto, the standard used in most like language modeling efforts. But then the flaws of BPE and BBP is like still like some words, rare words will still get like over fragmented, and then that also like promotes loss of information. Also, models will learn better representations for tokens that have longer subwords. So if I had like Masakani, for instance, like if I have just Masakani, like, and my model learn, like my model will learn like a better representation for Masakani than like learning representation for MAS and AK and HANE. And also like low resource languages could have like lower vocabulary allocation, because all of this, like building these tokenizers, is based on frequency. So languages that like have like less data in the pre-training data would mostly suffer. Also, languages unique scripts would also suffer, because like they cannot like benefit from subwords in other scripts. So now I just like did an overview of like the history of tokenization in NLP, going from word-based, character-based to subword segmentation. And now I will talk about like, like implications of subword segmentation with commercial language models. And this is very important because like, I mean, many people here use ChatGPT, yeah. And then, sometimes I've heard people say stuff like, oh, I got charged, this amount of money for processing the same text as an English speaker. Why is that so? So I'll talk about this now. So like I mentioned before, so in multilingual language models, subword tokenizers lead to, a disparity in fragmentation rates for different languages and different writing scripts. And like I said, commercial language models, they're like usually multilingual. They are not always multilingual, but sometimes they're multilingual. And then it means that languages with excess fragmentation. So if my tokenizer, if the vocabulary of my tokenizer is not like well balanced, the languages that would have like very high fragmentation rates will be represented by more tokens. So like that means like slower inference. That means the model cannot learn like good representations for them sometimes. And because these APIs or these like language models are usually paid, sometimes, I mean, like there's ChatGPT, there's GPT-4. I think GPT-4 is like, is paid, and ChatGPT is free something, but probably GPT-4 has, like better performance because it's a paid API. If you have like, more tokens in your input and the model has to generate more tokens like in your output, it means that you will be paying more than somebody that speaks a language with like less fragmentation rate. So let's take ChatGPT's tokenizer, for instance. So we have this, we have this sentence in English, and then this tokenizer is open source, by the way. So we have this tokenizer in this sentence in English, and then I just input it into ChatGPT's tokenizer, and I'm like, okay, tokenize this sentence for me. And at the end of the day, I have 30 tokens, and then you can see that most of the words still retain their full forms. So the colors here like indicate like the separation. If you see like a separation between like a full word, it means that like it's separated it into subwords. But like almost all the words here like are still retained. But then let's look at Japanese. So this is Japanese. So this is the same sentence but in Japanese, and you can see that like right now we have 94 tokens representing like the same information. So that's like 3x. Um, okay, then let's look at Swahili. So for Swahili, we have the same sentence still, but in Swahili we have 64 tokens. But then we would say Japanese is probably like, more resource than Swahili. So why do we have more tokens in Japanese than Swahili? Let's just hold the thought. Let's go to Telugu. Oh wow, we have 437 tokens. I mean, like if I needed to use the model in Telugu, like I would just go broke because I mean, like if I have to like, pay like up to like 10 times than an English speaker, like I mean, I would rather not use the API. Um, so what's the common issue here? Like we see that languages with non-Latin scripts generally suffer more from overfragmentation, like in this case with this particular tokenizer. Um, so this brings us back to like byte level subword segmentation. So there are lots of like writing systems in the world. Latin scripts, Arabic scripts, Amharic scripts, Cyrillic, Greek, Hebrew, Japanese, Korean script, and all that. But BBP or byte level BPE, it makes your vocabulary construction script agnostic, such that like your model is still able to process text like a test time that like process tokens a test time that it did not see during training. And so it means that like you can support like you can decide to just train your model on English and then test like later on Amharic. I mean, but it doesn't like necessarily translate to better quality. It just means that like the model can process it, which was not possible, or which is not possible with like word level tokenizers where you train on like one language and test on another language scripts, or even with like just like plain BPE that's based on like just character or like Unicode. Um, this is good, right? Like we can always like we can build you can build a model and keep on improving on it. Like we're happy and everyone is happy. But we see that like different scripts are encoded differently with BBP based tokenizers. And obviously, language script distribution in training corpora, like in training corpora, varies widely. Like we mostly have, if I go back to this slide, you'll see that like we mostly have, Latin script like languages. Like there are more Latin script languages than any other scripts in the world. So it means that, or even like online on the web. So it means that your like if we take like this like language models and look at like the vocabulary of their tokenizers, it would like mostly be dominated by Latin script languages or like Latin script words or Latin script characters or tokens or subwords. What are the effects of this, of this variation? Like, how does it, like, what does it mean, for like model performance, model utility, and all of this? So we did a study where we tried to like, answer like certain research questions. First of all, we wanted to see how like if like, all languages, convey the same information with the same number of tokens, with like, some of these tokenizers. And to also see that, okay, like when you have like, non-uniform tokenization rates, meaning that, language A has like, higher fragmentation rates than language B, like does it lead to like, like cost disparity for speakers of different languages? And also like, how does it affect the utility of the model? Right? Yeah, like we agree that with BBP, like we can train on Latin and then test later on Arabic. But does it like really mean that the model like learns good representations for these languages? And I think lastly, what are the socioeconomic implications of this like, cross-lingual cost and performance disparity on users? Um, so like a experimental setup, we focused on models, that were explicitly stated to be multilingual. It's one thing to build language models or have an API, like a commercial language model, and then come out and say that, oh, our models are being used in 100 countries by, people that speak 100 languages, and then advertise it like publicly to like, work well in these languages. And it's another thing to, still like train your model on all of these languages, but, just like leave people to assume. So like in this talk, I'll mostly focus on like the left part, like ChatGPT because of time. Um, Yeah, so to answer the first research question, right, like do all languages convey the same information with the same number of tokens? We just take a multilingual parallel corpus that covers about 200 languages. That's Flores. Um, Particularly because we want to control for content. We want to see if I have this sentence in English and I have this sentence in Amharic and I have this sentence in Swahili, like how many tokens do I get when I tokenize, like how does the model, like how many tokens does the model see? And then we decided to like, take these open source tokenizers from ChatGPT, from OpenAI, and then tokenize each sentence. And then we compute the average number of tokens per sentence in each language. So there are other ways that people, have tried to, measure fragmentation rates. There's like a measurement called fertility, where you take that, you use the ratio of like you use word boundaries. So like you use the ratio of like words, like number of words in your data set to the number of like resulting tokens after tokenizing. But for those of our experiments, really wanted to see like just like wanted to like just control, like use parallel text to just control for like same information. I have the same information. I don't care like how it's broken down into words. I just want the same thing across languages. And then we say that a language is more efficiently tokenized than another language if it uses fewer tokens per sentence on average. So like you can see the English example on the left and then the Japanese example on the right. So obviously like language English has like a more efficient tokenization than Japanese. So these are like, the assumptions that we make. So first of all, so we have this plot on the right side, where we compute like the average number of tokens per language, after tokenizing like this parallel corpus. So like we aggregate like the scores across like scripts and just take the average, in this particular plot. And then if you see here, you see that like Latin script languages are represented by fewer tokens, so less cost compared to like languages in other scripts. See languages on like the right end, like they have like very high bars, like going to like ×2 of Latin script. And then, okay, you can ask that, oh, maybe this disparity is due to training data imbalance. Like, yeah, of course, like maybe they mostly trained on Latin script languages. I had said before that, Latin script languages, dominate like the languages, like we have like more Latin script languages spoken in the world. And yeah, it's agreed, like ChatGPT was primarily trained with Latin script languages. But we can't like, ascertain what like it was trained on, like GPT-3 was trained on, because the trained details are not available. Like we don't have access to the model, we just have access to the tokenizer. But can we assume that, okay, its training data set is like, kind of like proportional to languages, like the data that is like languages that are represented in like publicly available like multilingual corpus like Common Crawl. So that's what we do, because we assume that all these models, like they're trained on like lots of text on the web, and Common Crawl is also like from like lots of text on the web, and then we believe that this should like be like maybe fairly representative of what like their training data could look like. So we sort languages in this plot based on their data size in Common Crawl. And if it was really, based on like training data, would expect that all languages on the left should have like lower bars, and then languages on the right should have like higher bars. But it's like, there's no pattern. Like the only pattern we see here is that Latin script languages are less fragmented. Even low resource Latin script languages are less fragmented. See Thai, for instance, even like see Vietnamese, see Russian. Russian is like close to like it's like the close like the second high resource language in Common Core, but it's has like higher bars than like some other languages. So then we're like, so what influences this non-uniformity of a tokenizer of the fragmentation rate across languages? So to answer this question, to like, just disentangle like this, like different factors, we decided to train these byte-based tokenizers on a variety of languages with diverse scripts and diverse vocabulary sizes. So what we did was, you get parallel corpora and take one language per script. So you have the same size of data in all of these languages, like in all of these languages, and you have one language per script. And then we believe that, this like allows us to compare across languages fairly. And what we do is now take these tokenizers that we've trained and use them to tokenize the text that they were trained on. And then we also compute the fragmentation rate like we had done before, like average number of tokens after tokenizing. And then we see that we still do not have like uniform like fragmentation rate across languages, even when we have like the same size of data. So we also see that like a lot of scripts are very sensitive to smaller vocabulary sizes, compared to like Latin and Hangul scripts. So it means that like even like Latin scripts can still do well with like very small vocabulary sizes. But like these other scripts, they still have like high fragmentation rates until like there's like this plateau when you increase the vocabulary size. So as much as we tried, we could still not achieve uniform fragmentation rate across all language scripts, even with large vocabulary sizes, and even with parallel data. So we, come to this, conclusion that like it's hard to like achieve this uniform fragmentation rates, and even like achieving this is not like only dependent on like the size of your pre-training data, but it's also like dependent on like the inherent properties of languages and their writing script. So to the next research question, so now we've seen that, yeah, like languages do not like convey the same information in the same number of tokens. So next, we see how like this non-uniform tokenization rates lead to cost disparities for speakers of different languages. So we all agree, that users are charged a fixed amount. So they charge you like a certain something dollar for a given number of inputs. So they charge you based on your inputs and they charge you based on your generated token. So like nobody cares if the generations make sense or not. You're just charged. So because like the same information is expressed using different number of tokens in different languages, just like we saw I don't know how many slides back. So the same text, like we have like people that speak Telugu, for instance, would like have more tokens. So what's the disparity in what users pay to use the API for different languages? So we try to like estimate like the cost based on like how much like OpenAI charges per token in like all of these languages and scripts. So here I have like by language family and by script, like the grouping is by language family and by script. And and we compute these costs relative to English. So we see that like languages that more heavily segmented, they have predictably high cost of usage. So languages that were on the right, also on the right in my previous plots, like the users in these languages will probably pay higher. And then we see that overall, the API costs are cheaper for Indo-European and Latin script languages compared to many non-Latin script languages. So it means that like if you do not speak like an Indo-European language that's Latin script, then you would definitely get charged more by these like API companies. So we've established that, so languages do not convey the same information with the same number of tokens. Yeah. If you have like more tokens, you pay more, irrespective of like, whatever utility you deserve. So now we ask the question, so even when we have like this non-uniform tokenization rates, like how does it affect models utility? Like do users still derive utility? Like, okay, yeah, you want me to pay 10 times more. Okay, I'll pay, but like, can I still like enjoy these models? Um, so usually, like I mentioned before, like models have a maximum number of tokens that they can handle. Like we call it the context size. So at the time, like we ran this experiment, ChatGPT could only take 4,096 tokens. So you couldn't like go past that. Um, but due to this non-uniform fragmentation rate across languages, it means that like the represent like each user can there's like a disparity in the amount of information that models can process in different languages. So if I have like times 10 fragmentation rate, it means I can only put like a tenth of what like an English speaker would like impute into the model. And then in context learning becomes difficult, right? Like within context learning, like you're showing your model like examples on how to like perform a task. But we like in this case it becomes difficult because if I can't even like fit like a full in context example into the model, then like my model, like the model probably will not be able to perform like the task. So this is an example of, when I try to um perform like a summarization task with in Amharic with just I think with two. So this data set is Excel sum. So with two in context examples. So you have the demonstration example. Like I have one says summary, then I put the no, it says like please summarize this article, and then you have the article, then you have the summary, and then you like have two like that, and then you put like the third one and then ask the same question, summarize this article. And then it's like the message you submitted was too long, please reload the conversation and submit something. So it means that like models become like only capable of zero shot prompting in some languages. And even for like tasks where you have like long documents, it's very possible that you cannot even fit like your full text or your full your full inputs into the model. Um, so this plot on my right, what we did here was, we tried to see like how much, like we had um, this data set. I think this is summarization here, and we tried to see like how much of like how many in context examples could you fit into the context size per language, and this is heavily dependent on like the tokenization, the fragmentation rate. And then if you see that, like for like a lot of languages, you can fit up to 10 in context examples. And then for like certain languages, like you can't even do zero shots. Like you can't, it means like you can't even put in, like you can't use it at all for like this kind of task, for this kind of languages. So this like, would affect performance of tasks that are complex, that would typically, perform better with in context learning. So this is just, trying to fit the your examples into the model. So then we did some experiments on like three tasks: summarization, fact verification, and so this like Excel sum is monolingual summarization. They are summarizing like in between like the same language. And then XFACT is like fact verification. It's also monolingual within like each language. So with fact verification, you have like a fact and you have like an evidence, and you're asking like if the fact is true or not based on the evidence you've provided. And then with cross sum, it's cross-lingual summarization. So you have like the article in like one language and you have the summary in another language. And then we can see that like on the right axis, we have like the number of in-context examples that each language can typically fit. And then on the left, on the y-axis, rather, we have like the performance of at each in context example. And then we typically see that like for like languages that have high fragmentation rates, like I mentioned before, sometimes you can't even fit like one complete demonstration. So you can only do zero shots, or even sometimes you can't even do zero shots. And we see that like there is consistent performance improvement as you increase the number of in-context examples from 0 shot to K. Like even if you have just one in-context example, the model benefits. But for cases where like there's no in-context example, it means that like you lose. Um, So what we've generally seen here is that like as a result of like this non-uniform fragmentation rates, utility is much lower for speakers of certain languages compared to like better represented languages. So even if this tokenizer would do well, like could process text at test time, like users still cannot like derive as much utility due to like issues in fragmentation. So the final question was, so given all of this, yeah, languages do not convey the same information, same number of tokens. Tokenization, the non-uniform tokenization rate leads to cost disparity. Some speakers will pay more than other speakers, and this, eventually affects model utility. So we try to see the the socioeconomic implications of this cross-lingual cost and performance disparity. Because it shows that like not only do I have to pay more, not only are these LLMs, these language models more expensive for certain languages, they're also less effective for them. And I mean, nobody tells you it's like, oh yeah, like this model doesn't perform so well on this
Hey,
language,
whatever.
like hence don't use it. Nobody like you just you find out yourself.
Hey, whatever.
So we try to
Okay, let's use the next 3 minutes. We're sort of running out of time.
Okay, yeah, I'm wrapping up.
Thank you.
Yeah, thank you. So we try to, correlate these measurements with socioeconomic indicators of language speakers as a proxy of like affordability of APIs. Like can speakers of languages with high fragmentation rates, can they like even afford these APIs to begin with? So HDI, Human Development Index, is like a proxy for like life expectancy, education, income per capita indicators that's used to rank countries in like tiers of like human development. And then we have this map that shows like how it varies all over the world. And typically like a lot of like developing countries usually have like lower HDIs. And then we see like very strong negative correlations between fragmentation rates per language and HDI. So in this plot here, we have like, we took like the top country in which a language is spoken, and then we did compute like, fragmentation rates. And then we try to correlate this with like the HDI of that country. And then we see that, the model's vocabulary is biased towards like users of more developed countries, like the countries that are like on the right side and just like below. We also still find like these negative correlations between like financial cost of like running experiments, model utility, HDI of the country in which a language is spoken. So typically people from like, less economically developed countries are overcharged at a fixed rate per token due to this excessive tokenization, but they would still like derive like less utility from the model. So to round up, what's the way forward? There are many things that could be done. Like first of all, like technological improvements in language models, like data balancing. Like look at your tokenizers and balance your data accordingly. Like it's not enough to just like just build tokenizers and assume that oh yeah, it should work well. Like try to like evaluate them, understand them. Also, I mean, there's a lot of work in like increasing context length of language models. There's Alibi, like there are lots of works like that. But this would still not like alleviate like the cost disparity. It just means that like I would have more tokens and yeah, I'll be able to like feed them into the model, but I will still pay more. And also I think one like very like important thing to note is transparency in API limitations. Like language model API providers should be more transparent about like the flaws and biases in their models, particularly when describing their multilingual capabilities. It's not enough to just say our model is multilingual. It works well. Like who suffers from it? Like who gains from it? Because usually, like I mean, I can bet that like most of the users of ChatGPT, for instance, do not even know what like a language model is, or do not even know what a neural network is. So like they do not understand how these models work, and then they could be unfairly charged higher prices if they keep on using these models in their native languages. Also, I guess we believe that higher API costs for certain languages in underprivileged communities could risk excluding many populations from using these technologies. So it's probably important, to develop like pricing policies based on language regions, while also accounting for model performance and like language specific benchmarks. Thank you. Yeah, I think that's all.
Thank you, Reva.
Can I stop sharing my screen?
Yes, you can stop sharing your screen. We only have time for one question. Is there a question in the audience? You are standing between them and lunch, so.
Oh, I'm so sorry.
There are no questions in the room, so I'm gonna release people for lunch. Let's just give Oreva one other round. Thank you so much, Oreva, for making time for us.
Yeah, thank you too.
All right.
Bye.
Bye-bye. So you have a very short lunch. We shall start at 1:30 with a panel session where Oreva, Marshall, Monojit, and Paul will be talking to us about multilingual models. So let's hurry up and eat, then come back.